Today's lesson is the beginning of a new unit, and that new unit is on polynomials. Something that you're already, you have some familiarity with. Polynomials are something you've been dealing with essentially since you started looking at equations of straight lines. And we'll start with that. So we already have these two familiar functions. I've written them in a generic form, something that students are not always the most comfortable with, but as you progress through mathematics, more and more often you're going to be working in terms of these generic or more abstract representations. So it's something you do need to become comfortable with. So the generic representation of a linear function is y equals ax plus b. Obviously x is our independent variable, y is our dependent, and then the a and b are simply numeric coefficients that haven't been defined yet. And these can be any real number. In the case of something being linear, we assume that this a, actually in this case it doesn't matter, these can be any number including 0. Down here on the quadratic, we assume a is not equal to 0, because if a was equal to 0, then that would make the quadratic term turn into 0, which would reduce this back to a linear, which is not what we're looking to have happen. Now, as far as order or degree, these are two terms that are interchangeable when it comes to these. When we talk about the order of an equation, we're looking for the highest value in the exponent of the independent variable. And that assumes you've got this written in the form. Actually, it doesn't actually matter. It's the highest order in the exponent of any variable. That's the easier way to think of it. Here you can see that the exponent of y is 1 in actually all of the representations. Here we have x to the 1, and that's the only independent variable x, so this is degree or order 1. Here we have an x squared, we have a y to the 1, we have an x squared, we have an x to the 1, and then where you have a constant, the degree there, just to remind you, anything to the exponent 0 is simply equal to the constant 1. So this, for example, is the same as b times x to the 0, because this is just b times 1. And so a constant, if we just have a number, for example, if I just had y equals a constant, y equals c, that would be a degree of 0. Here we have a degree of 1. Here we have a degree of 2. If I go further than this, so here's our linear, here's our quadratic, which would be graphed as a parabola. Then we introduce the generic form for a cubic, and so you can see that that is order 3, and you can probably see where I'm going to go from there. Quartic, cubic, quartic obviously implies, the name implies 4. Quintic, the name does imply 5, but it might be a name that you're not so familiar with. Now, what is this going to look like? It's really just extending what we've already done here. So a quartic generally is going to be ax to the 4 plus bx cubed plus cx squared plus dx plus e. And quintic is going to be ax to the 5 plus bx to the 4 plus cx cubed plus dx squared plus ex plus f. And the letters we use here are arbitrary. Obviously, I'm just doing these in alphabetical order. Normally, you're not actually going to see anything beyond maybe this order 3 or 4. You can see it gets quite tedious to be writing these things out all the time. In general, and once again, this is a level of abstraction that's even one step further than what I talked about at the top of the lesson. So in general, any polynomial function can be represented in a standard form, and this is that generic way of representing any polynomial function, whether it's a constant or whether it's linear or whether it's a quintic order 5 or even higher orders than that. And you can see that I've got this generic notation, and I also am using some set notation similar to what we've done with domain and range, so that I can define some different elements. For example, I say that all of the coefficients from a0 all the way up to an, assuming there are n terms here, those are all real numbers, and each of the indices and each of the exponents, that's an important distinction to make. If we're talking about a polynomial, all of the exponents are going to be natural numbers, 0, 1, 2, sorry, not even 0, 1, 2, 3, 4, 5, and so on. And the same thing is true here for the coefficients, except for, well, that actually makes me think, rather than saying natural numbers, perhaps I should have said whole numbers. Simply because you could argue that the exponent here is essentially x to the 0, and obviously this index is 0, which wouldn't be in the natural numbers. Now, you're not going to have to remember, you're not going to have to be able to reproduce this definition. It's more important that you understand it. So please forgive that small modification I just made there. Okay. Now, in this definition, I've said an is the leading coefficient, so that's the coefficient of the highest order term, and the degree is going to be the value of the highest exponent. So in this case, we have an order n. We're assuming that this is non-zero, and that's actually something I wanted to add in here, which is that an is not equal to 0. The highest order coefficient is not 0. Otherwise, that bumps us down one order. And then if that one were 0, it would bump us down. It would bump us down. So we assume that this one is the highest order term, is non-zero. That means that n is the degree of this overall polynomial. These other terms can all be 0. It doesn't matter. Only the highest order term defines the degree of the polynomial. And when we write these things, we write them in descending order of the powers of x. So that just means, and that's a convention that I'm sure that you've already been introduced to, which is we always write our highest exponent first, and then we descend all the way down to a constant if there is one. Now, this is something that you should have encountered in grade 10, which is if you have a table of values and you're looking at, for example, a table of values and you take first differences. If your first differences are constant, well, that occurs if you have a linear relation. Second differences will be constant for, well, they won't be constant for something that's linear, they will be constant for a quadratic. And that continues to be true. That pattern continues to be true. So from linear, we do first differences. Quadratic, we're looking for second differences to be constant. So if we had an unknown relation, and we had it in terms of a table of values, we could use these finite differences, more and more of them. We could do first differences, second differences, third, fourth, fifth, sixth differences, until we found that they were constant. If we have an order n polynomial, then it's going to be the nth difference that's constant. So if it's an order 5, which is a quintic, then that's going to be fifth differences that we have to go to. Now, that can be a problem just because of when you're trying to take first and second and third differences, you have to have enough data points in your table to allow you to do that. The domain for these is always x member of R. This is for any polynomial. Any polynomial will accept any number as input. The range is going to depend on the graph, both the parent function of the graph and any transformations that have been applied. And we'll take a look at some examples of those in a moment. Now, just again, this idea of working in the abstract, what I actually want to do here, you'll notice I don't have any values for my constants, for my coefficients here. So I'm just going to create a table of values just to illustrate something. When x is equal to 0, what is this equal to? Since I don't know the coefficients a and b, that would mean that this is simply equal to b. When x is equal to 1, that would be a times 1 plus b, so that's a plus b. When x is equal to 2, we end up with 2a plus b, 3a plus b, 4a plus b, 5a plus b. Let's take a look at our first differences, which is a short form for that is this delta y. a plus b minus b, what does that leave me? That simply leaves me a. 2a plus b minus a plus b, well, b minus b is 0. 2a minus a leaves me a. 3a plus b minus 2a plus b, and of course you can see where this is going and where it should be going. Each of these first differences gives me a value a. Regardless of what this constant is, my first differences will be constant because my first differences are always a, no matter what a is. So let's do the same thing here for the quadratic. I'm sure you can anticipate where this is going to go. So in this case, if I put if I put x equals 0, I end up just with the constant c. If I put x equals 1, I end up with a plus b plus c. For 2, squaring the 2, that's going to become 4a plus 2b plus c. 9a plus 3b plus c. 16a plus 4b plus c. And 25a plus 5b plus c. Now this one is quadratic, we know that in advance, so when I take my first differences, I should find they are not all the same. A plus b plus c minus c is just a plus b. Be more careful here, simple enough to do. The c minus c is equal to 0. 4a minus a, let's do it this way. 4a minus a is 3a. 2b minus b is b, and c minus c is 0. 9a minus 4a is 5a. 3b minus 2b is b, and c minus c is 0. This one works out to be 7a plus b, and this one works out to be 9a plus b. And then we take, so obviously first differences are not the same. Take a look at second differences. We end up with 3a minus a is 2a, b minus b is 0. 5a minus 3a is 2a, b minus b is 0. 2a, 2a. Second differences are all constant, even though I've got this very generic form. This is a quadratic. And finally, I'm just going to show you some examples, some things you're already familiar with. For example, here is the linear, which has a parent function y equal x. And then we have some transformed. We don't normally think of transforming straight lines, but we're still doing that. We can vertically stretch or compress it. The vertical stretch or compression essentially is this slope, y equals mx plus b. So this m value is a vertical stretch or compression or reflection. And this b value, which is our y-intercept, well, that is a vertical shift up or down. In this case, you can see b is equal to 1. Well, that means that this point at 0, 0 has been shifted up here to 1. So it's still a transformation. And you're going to need an understanding not only of the parent function, but also of the transformations in order to determine domain and range. Now in this case, for all three of these that I've shown you, the domain and range, both of them are just x member of R. Any x value can produce, well, eventually if we put in all possible x values, we will get all possible y values. And the reason is because all of these graphs extend left and right to positive and negative infinity, and they also extend up and down to positive and negative infinity. But that is not always going to be the case. Take a look at a quadratic. Here's the parent function, the dotted line. And you can see through different transformations, I've moved the location of the vertex. I've done a vertical stretch here. I've done a vertical compression here. But I've also done a vertical reflection on this one. And so now domain and range takes on a different meaning. In all cases here, the domain is x member of R. And that's fine. That's what I said earlier in the note. For all polynomials, the domain will be x member of R. But your range is actually going to vary. For the parent function, what's our range? What are the possible y values? Well, they're all values greater than or equal to 0. Whereas here, for this blue one, my range is y member of R. Y is, in this case, it opens up, so it's greater than or equal to -3. And for the red one, I have the range is y member of R. And in this case, here's the new vertex, and that's at -1. So this one is y less than or equal to -1. So you do have to, and maybe a quick sketch, you need to be familiar with what the changes are here. So this one was quadratic, that's order 2. Here is a cubic. So there's that dotted line, that's the parent function. And then you've got the blue one here is a transformation. Now we don't have the vertex to key onto as easily. You might think, oh, well, it's the middle part of these different graphs, but depending on how the cubic is formed, that may or may not apply. So don't make assumptions about that. But there are a couple of other things you might take note of here with the cubic, and the most obvious one I want to point out to you, so this one's order 3. Notice that the cubic, both in the parent function and with these transformed functions, notice that it goes up to infinity on one side and down to -infinity. This other one has been transformed, it's been reflected, but this one's going up to infinity on the left side and down to -infinity on the right. So in both cases here, our domain is just x member of R, and our range is y member of R. And that's applicable to the parent function and to all the transformations. And this one is an odd function in the sense that it's, the order is odd. It's an odd ordered order 3. Now we switch back to an even, which is like our parabola. And what do we notice about the parabola? Well, the parabola, because it either opens up or down, had a restriction on the domain. Well, take a look at this quartic. It also opens up or down. The parent function actually looks very much like a parabola, but depending on how the transformations are done and how the equation is set up, you can actually get these extra wiggles in there. So it's not as simple as a parabola, but it still has this notion of opening. The blue one here opens up, which means it's going to have an absolute minimum. The red one here opens down. It's been vertically reflected, but it still has an absolute maximum. Unfortunately, in this case, this one is not an easy one to be able to read. We would only be able to estimate what the limit is on the range for this one. Let's see if I have a order 5 here. I do. Now that we're back to an order 5, which is an odd number for the order, notice that once again, whether it's the parent or this blue one or this red one, at one end it's stretching to positive infinity here and here, at the other end stretching to -infinity here and here, which means that this one, once again, domain is all real numbers and the range is all real numbers. In general, the order of the polynomial tells you how many potential wiggles you might have. You won't always have that number. As you can see, this parent function, even though this is order 5, the parent function doesn't have any of those wiggles. It just has this one change in direction. Whereas these transformed ones, let's look at this red one, it's a little bit easier. You can see we come down and then we're going up. And then we're going down again, and then we're going up again, and then we're going down again. And that is a product of the fact that it is order 5. And I believe that is it for your first introduction to higher order polynomials.